Hey guys, so in my game of Fractal Skies, I ended up creating a water physics model that I haven't been able to find elsewhere on the internet. So as you can see on my screen right here, what we have right here is a 2D water physics simulation. The first reservoir right here is a bit taller than the second one. And then we have this little pipe, and this here will demonstrate what we'll be going through today. So the first thing with water physics that I usually encounter is that it doesn't create a nice waterfall effect. So when you have water that overspills, it ends up just kind of doing a pyramid and going down almost horizontally or diagonally. In my physics model, we'll be creating something that has a waterfall effect. So you can see the water just falls down pretty straight on the side. Uh, The other thing is once it fills up all the way over the top. If I were to drain one reservoir, the other one stays roughly about the same height. The other issue that I see usually with physics models is back pressure. So right here we got some water, and if I were to add additional water in, it would have to go up the pipe and then back out down. Typically, water physics models say if I'm a higher elevation, don't take from below me. But in this water physics, we do want to create a pressure model so that if I were to release or open up this little gate right here, we can see that the pressure of water on one side pushed up the water onto the other. And as we add more water, we can see it acts almost as a pipe. And what we can do here is add a whole bunch of water, open it up, and see it all drain to a specific level. We can then close it and drain one side. And so you can see that this water physics model actually behaves quite similarly to real world water. And for a kind of voxel game, this ends up being quite useful. So I'll go from scratch right here and start from an empty board. So on the wrong system, let's start up this one here. So on an empty board, we don't have any controls, any water, whatnot. We just have a simple grid. What we'll want to do is create a grid of cells. So the cell would contain a water level. We're also going to keep track of the maximum water allowed in a particular cell. And we want to see whether the cell is blocking or not. So now that we have these three values, we can start setting up our array. So let's go here. Okay, so we got a simple iterator over here. And to display water quickly, I'll just set a default water level. And we'll update the render function right here to display the water level. So here we'll want to fill the water level with a blue color. And we'll want it somewhat transparent. Then we'll update the screen with the water height. Now we can compute the water height by finding the water level for this cell. So let's find the index for the cell. Dot water level. So we got the current water level of the cell, and we want to divide it by the max water level. Then we want to scale this by the scale of the grid, and now we have a water level right here. So let's only do this if the cell has water. Otherwise, well, it wouldn't do anything. It would show 0 over max level. So now we see the grid does contain the water level for each cell on the grid. So let's go ahead and remove this. And in order to interact with the application much more easily, we are going to add mouse controls. To simplify computing the index, I'll create a simple coordinate system to help us with that. We can use the coordinate system for a couple things later on, so also help us down the line. So let's go here and create some kind of coordinate system where we pass in the x and y coordinates, and it will compute the coordinate that we need. So here we got the height, or y times the width of the grid plus x. So this here is a simple formula for calculating the index in a two-dimensional array. And let's initialize our coordinates so that we have these values handy for us. And we go up here and we instantiate our coordinates. All right, let's replace the coordinates down here so we're consistent everywhere. Now that we know where we press the mouse, we can start adding controls to the grid here. All right, so now we should be able to add water, remove water, and we currently don't render blocking, so let's go ahead and do that as well. All right, so we can see water cells, we can remove water cells, we can remove blocking cells. That will allow us to set up our scenario where we have, let's say, a reservoir, and we're trying to contain all the water inside of it. At the moment, the water physics doesn't exist, so the water isn't flowing anywhere, but at least we can visualize it so that we can quite simply start building it. Because we're building this for understanding reasons, I'm not going to build it for the performance that would be required for a game engine. I'll cover some optimizations for performance a little bit later, but I'll be building this more for demonstration. Now, there's three main modes that we should be considering for demonstration. There's the real time of how this would realistically look inside of a game engine. We have a resolution, which is like every time that you would resolve the water movement, you could render at that point. And then the third way of having or displaying things would be steps. So every step inside our algorithm could be displayed independently so that we can see what is happening at the lowest level. And we can tune this up so that I can control which mode I want to use based on the key press. All right, so we're good to go here. Okay, so we have an infinite loop right here. If the mode is step, then I want to pretty much get out of here all the time. If the mode is I'll deal with these other ones a little bit later. I think we're good here. So the first thing that we have to do is see, okay, I have an entire area, entire grid space, and I want to evaluate all of these cells as individual candidates. So here we'll have some kind of process to calculate candidates. Now, candidates on a very basic level would just be every tile in the game. We can definitely improve on the performance of this later, but for now, for demonstration reasons, we're going to just build this incrementally. The first thing we want to do is remove anything that is blocking. We have to create a new list here of candidates. So now that we have a list, we should be able to calculate the candidates for that list. So if the target index equals -1, and the candidates list is empty, what we want to do is calculate candidates. As if the target index is -1 and the candidates list is not empty, then we grab our first candidate. So here we can use a queue, and let's make that a linked list. And for now, we're not going to be processing that target list, so let's just eliminate it from the option. What I want to do here in the rendering is if I have a target, then I want to display that particular cell a specific color. So if the index is equal to the target index, I'll be displaying the box red. So we should see that the bottom right here is being processed. We can see it go by. And it's not going to resolve a whole lot because right now there's no logic. Even if there was water around this point, it wouldn't actually do anything. But it allows us to start visualizing things a little bit more on what's happening within our process. So here, we got our candidates. If we don't have a target index, we would start removing it from this candidate list. And here is where we start computing, okay, well, I have a target. I know how to move from here. So let's start calculating that. So what we're going to do right here is a pathfinding algorithm that goes from the lowest water cell to the highest water cell, and we're going to grab some of that water from the highest and pull it down to the lowest level. So here we need to start building a pathfinding algorithm. So if we visited all cells, then we know our target had not been met. However, if there is still something in the unvisited cells, we can take the next one and start processing on it. So for convention reasons, I'll be calling the location that the water is going to the target, and the location that the water is coming from the source. So here, when we talk about the water source, we're talking about, it's a bit of a reversal of pathfinding, usually called the destination the target and the origin as the source. But in this case, we're moving from the destination to the origin. So when I was originally implementing this, I would constantly get confused between the water source versus the water target and whatnot. So I'm kind of reversing a little bit the vocabulary here, but it'll help me understand what's happening. So here, when we create a new index, what we want to know is what is the water potential threshold. So this here will be the water potential at the target index plus 2. So let's go ahead and create a field for this. It'll just be an integer and create some math here to calculate the potential. Okay, so the water potential will be the coordinates, the y coordinate of this cell index multiplied by the max water level plus 1, and then we add the water level at the index. Now I'll break this down in its individual components in a second here. Let me just create my conversion tools. So here, what I want to do here is that the cells that are higher up on the grid would always have a water potential higher than the row below it. However, if the row below it was at the maximum level, it would reach the very height. And if I don't add 1, then if the top cell right here had 0 water level and this one here had maximum water level, they would have the same water potential. And I always want things to flow from the higher grid to the lower cells in the grid. So for that reason, I wanted to add a plus 1 over here to the y, and that would create the full water potential of my entire grid. And then we just add the water level right here. As to this magical plus 2, what happens right here is if you have a cell that has a water level 4 and a cell that has a water level 5 and they're like adjacent to each other, what you would see is that the first round we would try to push the water from, actually this way, we would push it from 5 to 4, And then the next time we process, it would go in the opposite direction. So you would constantly see this water going back up and down, and it wouldn't really resolve itself. By adding two, we mitigate that problem that uh, we will always be decreasing the potential when we move from one source to the other. So here we got the water potential, and what we want to do right here is find the water potential of the source index. And if that water potential is greater or equal to the water potential threshold, then we found a source. And at that point, we can do something pretty simple. We grab the source index, we subtract the water, and we grab the target index and we increase it. At that point, we found our target, and so we can remove it down here. Now this here is a relatively naive implementation, and we'll go into this a little bit more. Okay, so yeah, so we're not finding the water potential at the moment because the only unvisited cell that we have was the one that we added up here. What we have to say that is that if this cell right here isn't meeting our water potential, then we have to visit the neighboring cells. So here I'm doing a little trick with the index. So instead of calculating this mathematical equation, what I can do is, because I know every increase in y would result in an increase of the index by width, I can increase it by width directly. And similarly, if I were to decrease the y by 1, I would know that that would correspond to a decrease in width on the index. So I don't have to compute the full value here. I can use this little math trick. As long as I know my edge cases, I'm fine with this. So right here I have my neighbors, and what I need to do right here is say if the neighbor, so I have visited cells, and actually let's just go directly from came from. So let's create a new map right here for came from. And what we're going to say right here is if we found a neighbor, and that neighbor is some kind of water neighbor, then what we're going to do is say that our source index, or rather our neighbor came from our source index, and we want to add that neighbor to our unvisited list. Now, isWater is a pretty simple formula right here. Let's just keep this as index. So a particular index is considered water if the water level is greater than 0. And so we only want to navigate through the map through adjacent water cells. If there's an empty cell, we're not going to consider it as a source for water, since that cell itself would have to be filled first. This allows us to iterate over our adjacent cells, and then we're going to iterate over that full list. So let's go here and create 2 new states. So if in contains, so we're going to show unvisited cells by a red background here. Let's make it slightly less red. So something like this. And anything that came from, we're going to make it a little bit brighter, but not so red. So let's see what this here gives us. Okay, so we see that we're not clearing the came from whenever we're finding out that our target index gets reset. So here we need to clear our came from, and we also need to clear our unvisited cells. All right, we're still having an issue here. Okay, so we also need to clear it up here where we run out of cells. Now you'll notice here that as we iterate over, we're going to start grabbing and we're going to backtrack all the way to find additional cells. There's 2 things that there's an issue here, is that we're not grabbing as much as we can, and we're kind of like pulling in the water from very far locations all the way to here. We don't want both behaviors, so we can see that our pathfinding algorithm works. However, we have to start moving this code into a priority queue so that we can get the highest priority, then go from there. I'll show you what I mean in a second here. So we got our candidates queue, and our candidates queue right now is just a linked list. What I want to do is make this a priority queue where if we get 2 values, what I want to return is the lowest of the potential values. Now, what I do right here is that whenever we find a source target, we change the potential of both the source target and the source and the target. So what we want to do right here is for the candidates, we all want to remove the source index and add it back again. This will mean that the location that the source index will be in that list will be refreshed, since we modified the potential right here, the water potential. We also want to add back the target index, and that is because we're only doing this for 1 level at a time, and we want to iterate on this until the full water level has been consumed rather than each individual one. With this priority queue, what happens is that the lowest priority will have the next chance of grabbing additional water, and it will balance out the water falling into a more even distribution. So let's go right ahead here and start showing what that looks like. So we're going to see that we're going to reprocess a lot of the same cells multiple times until we fulfill the criteria that we were looking to achieve. Now we still notice that this behavior right here, we end up pulling water from very long locations. And the problem with that is that this cell right here will contain additional neighbors didn't that didn't have water in the previous iteration of the game, but now does. So it is a valid neighbor, and we need to block that somehow. The way we end up blocking that portion is by considering a maximum flow capable of occurring at any given point. So here, when we calculate flow, we want to only move as much water as we had. So if we had 5 water, we couldn't possibly move additional water through that amount. It creates a certain limitation of how much water can flow through a particular tile. And so let's go ahead and implement that. So now instead of saying if our neighbor is water, what we want to say is if our neighbor can flow water. So let's go right here and pass in the neighbor and say flow is greater than 0. This here wouldn't help very much. Well, it will, actually. Let's see here when we... Oh. The flow doesn't get computed when I put down tiles, so let's go ahead and make this flow also equal to max level so that I don't have to actually update this while it is running. So here, if I add additional water, you can see that it now flows, and it doesn't like go way off grid because the cells below it contained no flow at all, so it couldn't possibly pass through. We can see now that our water physics is flowing properly, but it's still taking a huge amount of time to compute everything. So there's 2 issues right here is that when I absorbed water from the source, I didn't actually decrement the flow. So let's find where my algorithm is. So here on my grid, source index, flow, let's subtract the flow right here. So now if we have something like this, we can see that we're pulling in from higher cells, but once we hit the higher cells, it won't go downwards like it did before. So we're going through every single possibility, and this is a bit time consuming to look through the entire space of this grid. So what we're going to do here is refine how we calculate candidates. So instead of just adding them to the list, let's just make sure that the candidate is water or is neighboring water. So if you're not neighboring water, you couldn't possibly get any water yourself since the neighbors would have a flow of 0. So what we can do right here is just iterate over the neighbors, and we have our coordinate system that could provide our neighbors for us. And if one, I'm not sure why my keyboard's acting up at the moment. Okay, so if our neighbor has water, then we want to consider it as neighboring water. And now when we process the loops, we'll see that we only process things within proximity of water cells. And we saw that we just reset here to the next iteration. So this here is a basic implementation, but it takes a bit long to present ideas. And as we develop it even further, it'll be a bit of a mess. So let's start implementing these other 2 modes that we talked about, the real time and the resolution. So let's start with the resolution here. So the resolution is, I don't want to see how we process the map as it's progressing. What I want to do is find out exactly, I just want to see the water movement every step of the way. So let's go back to here. So by the time I'm calculating new candidates, I've effectively ran through an entire loop. So what I can do right here is if my mode equals real time, then I break at this level here. The other portion right here is if I went through every possibility and found no cells that were adjacent to it, it would match the resolution. As well, if I find that my source, if I find a source for my target water cell, then I've also hit my resolution. So let's see how this here works. So this here is resolution, where you can actually see water moving each step of the way. And then if I go real time, I can start like seeing how well it works if I were to start pulling in additional water. So let's see how well we're doing with this, with the waterfall effect and the back pressure. So here, if I increase the water, we eventually have a single stream of water falling down. Now the second test is, does water flow back up? So here, if I open this up, we'll see that the water actually came back out. So this here actually fulfills the two criteria that we were looking for. However, there's an additional kind of bug that occurs. Let's just clear this out. So if we have an entry right here, let's clean this up here. Okay, let's fill this with water. Okay, now I'm going at each step of the way, and you'll see it process. This is okay. Seems like it's picking any index around here. I'm not entirely sure I like this. Let's see here. So we got the candidates, and the candidates should be based on the potential level. Does seem to be processing fine here. It seems to go here, 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 and here. That's not what I was expecting. Let's go back to the water potential here. We should be organizing our code based on the water potential. Maybe it's the coordinate. Oh, that's fine. The behavior is fine. We're still calculating from bottom going up. So I'm not too sure if that's something to worry about at the moment. But it's definitely something to keep an eye out for later. All right, so I'll just move on to the next step. Just be cautious about that behavior. So what's happening right here, if we go into a slower motion, we're going to see a weird behavior when we move from one reservoir to the other. So here, if I were to open this little hatch, what happens is my resolution starts going through from here and then moves on to this portion right here. Yeah, I'm definitely having weird behaviors. Okay, let's go and see here. When my real time hits here, that's fine. By the time I hit here, that's fine. Then if I hit these two portions right here, we're fine. Yeah. Okay, let's try this again. Maybe I'm reading this wrong. Yeah, it seems to be almost random. Okay, that's just weird. Let's see. Okay, so the first thing we want to do right here is if the water is already at the highest level at a certain location, then we don't want to compute this particular index. So let's see, target index. not equal to this. Let's make this a potential index, and then only set the target index if it hits the potential index. Okay, that appears to be fine. Let's just remove all this. Let's see. Okay, so the behavior that was happening before was just because the cell right here would go above its maximum water, and it would try to grab water from above until basically all of the cells would be at the same potential water potential, and that wasn't what we were wanting, and it was screwing up with my water potential algorithm. But here we can see that once that has been resolved, it seems to work relatively well. So let's go ahead and clear this out. Let's clear all this water out, and let's remove this. So one of the problems that we have right now in our current implementation is that if we have two reservoirs and you move from one to the other, then we'd be doing it in a bit of a weird kind of approach where it would kind of like go upwards and sideways at the same time. So we don't see it in the very first portion right here. Actually, let's go in resolution mode. So we're going to see that the water will actually go upwards over here and sideways at the same time, and that's not what we were expecting. The water that should be passing through this little entry point right here should be pushed all the way down to the end over here before it ever goes up. Otherwise, we get this weird behavior where water would start going up in this kind of triangle formation until it reaches a certain like level potential over here, and then it kind of evens out. It doesn't go above we might see it in the next level right here. Yeah, and now it's starting to even out. It kind of works pretty nicely, but it's not exactly what we were thinking. So let's try to debug this a little bit. So when we have a water level here, what we want to also have is a flow height. And this will keep track of how much water is capable of flowing at a particular level, or at a particular point. So let's go ahead and have this flow height here displayed, as well as the water height. Now, in order not to hide one with the other, I'm going to just offset the x-axis by by a certain margin so that we only see a bar on the side instead. So here we should see the bars on the side, and at this point it's leveling out. Okay, let's just remove all of this and create a basin. Okay. So here we notice that the height or the water flow is decreasing when the water moves. So let's go ahead and create a little bit of a little snippet here. And we'll see that the water on the side here is decreasing its flow rate accordingly. But what happens here is that we're only considering the flow from the source to the target. And because of that, when we hit this situation, the flow in this little section right here decreases to effectively nothing, but we're still able to grab water outside over here. And that's why this flow level here never decreases to zero and blocks out the, the flow of traffic over here. So what we need to do is go ahead and over here, instead of decreasing the flow, what we want to do is decrease the flow of every cell that was in the path to find a higher potential. So here we have the came from map, and what we can say is that if it didn't come from nowhere, which means it would be the root node, we want to decrease the flow. So here we have our decreased flow. Let's move it slightly away from this water level change. Now what would happen is if we had this this basin, and let's just add a whole lot of water. Let's make it real time. Let's make it resolution time. Now when I open this level here, you'll see that the water flow is 0. Actually, let's see here. Doesn't seem to be decreasing. Let's look at the algorithm again. Oh, I'm reducing the source by the number of times that number of path. All right, so let's try this again. We have here, let's set up our basin and open up this. So you'll see here that this pipe, whenever it tries to, still not working. Still reducing it from this level up here though. Interesting. Ah, there we go. Should be not equal, not equal, equal. Okay, third time's the charm, eh? So fill the basin. Let's remove the water here. Now let's see what happens. So here we notice that every place the water flows through decreases its flow rate. So now we're at this point and it completely blocks out this little entry from receiving any more flow. And so what we see here is a cascading effect that if I'm trying to push water up here, I'm taking it from the flow from all adjacent fields. And we can see it now follows that pattern that we were speaking of earlier. So if I start filling it up, it'll fill up more gradually. We can see it more if we expand this out quite a bit more and make this really high and remove this portion right here, fill this up, and now let's go. You can see it fill sideways before it starts filling up. So we'll fill the bottom of the basin before it starts filling up to the top of the basin. And that's kind of like what we were expecting. Now there's a certain problem with this kind of algorithm, and basically it'll show right here. Every single tile ends up doing a full scan of the entire neighboring water, and this here ends up taking a lot of computational power. If you're doing a 3D map and you have massive area, let's say a pond or a lake, this would end up costing a significant amount of time in order to achieve basically nothing. It doesn't do anything at this level here. It's in a stable state. So when it's in a stable state, we can save a lot of processing power by eliminating a lot of computations. So if we visited every cell and from the lowest potential, we couldn't find any cell that was higher potential that we could steal from. It means that the effectively everything has reached a stable state, and anything connected to the lowest cell won't be able to find anything any higher than what you already computed. So what we can do right here is if we reach a state where we couldn't find any cell that we could steal from, then what we can actually say is that anything in this key set will never be able to reach a higher stable state. So what we can say is just eliminate the flow here entirely. So if I go ahead and I fill this basin up, and then I look at how the step process is working, the first one will effectively do a full scan, but then the others are just going, they won't find any neighboring cells that have any flow. So we can see the flow here on the side. It's currently as high as it can be, but as soon as the first one passes through, you effectively get no additional computation power for traversing the grid. And so that allows us to have a pretty simple stable state algorithm that doesn't compute more than it needs to. So the other optimization that you can do here is, let's say you have this full basin filled up, and when we clear up this level right here, we know that the higher potential is always above us. So if we have two levels right here where we have a side and a top, we would probably always want to favor above us. So let's go ahead and implement that. What happens right here is when we calculate the neighbors, we should just calculate the ones that are above us before anything else. And the ones that are below us, let's keep that to the last, because if we're going downwards, it means that we haven't found anything that was beside us that was any higher potential. Now, when we run this code right here, and we have our double slit basin here, we fill this up with water, and let me clear this out. What you're going to see is that the water will travel upwards. So each cell will grab from the above, and you'll see that the scan for what happens for more water will be very limited to a very specific area. So we're not looking very far for higher potential water. We're not doing a full scan. And this here is pretty much why we started from the destination rather than the target. If I was starting from up here and then trying to find a lower potential, I'd have to traverse the entire graph in order to find the next highest space. But if I start from the lowest, I can compute the next highest pretty effectively by just traversing a small little portion of code. And pretty much once you're at the very end, you would do a full scan of one of the nodes that would compute everything. So here we're pretty short, or we don't scan a whole lot, but then by the time we're up here scanning, we're scanning a very little amount of cells. Now you could improve this algorithm by using A star. So right now I'm doing a flood field kind of search. If I were to have the heuristic that the higher up you go, the higher your potential or the likelihood of potential, it would just go down. It would search this whole area pretty extensively, but then it would try to go right up here to the highest potential area. And we can calculate the heuristics pretty easily. Basically, we're trying to have the target of the water potential plus 2, that water threshold, and anything lower, well, we can calculate that potential directly. What we do is that difference between each cell's potential to the threshold potential, that would be your heuristic, and the cost to get to that cell would be your full cost. So you can calculate your A star computation that way. I think this here is generally performant enough, and it has all the great behaviors of water physics. So let's see. Another optimization that I did during my game of Fractured Skies is in here when I calculated the water potential. So I go down here and I fill it up. And what I do right here is if for every water level, you kind of have to redo this whole computation. Let's just clear out the bottom here. So here we see that there's a flood field, and we have to do this for roughly the amount of water level you have. So if you decrease the water level from this maximum of 16 to 4, you can achieve quite a lot of value by drastically reducing the computation cost. So here now I have my water level, I top it up, and now when I open up this little slot right here, you'll notice that this algorithm works a lot faster now because I don't have to compute every single entry. I can say move water 4 chunks at a time. I don't need to move it more than that. If you really want to reduce this, you could reduce it to 1, but then you get a bit of a weird behavior here. Let's just do this. So you still get the water flowing, but it either flows completely or it doesn't flow at all. So you might see like huge increases of your water level. But this here could work for your game. I don't know. It's very possible, and you still get fully functional water physics. It's just that it's not going to be as granular as you may want. So in my particular game, I chose number 4 because it represents a couple different game states. So let's just. So here we got a couple levels. Okay, so we got all 4 levels here. So when it's full like this, my character would be drowning. So they would have to have a little bit of air in order to breathe. At the level of, let's say, 3 water level, my characters would have to move through this through like swimming or other kind of activities. If it's at level 2 right here, they would be able to walk through it, but it would slow down movement. And at 1 level, this is where water would start evaporating. It's not so much that it would constrain them. It might just a little bit, but it wouldn't really be a massive impact to the characters. It would just be a little puddle. So typically I would stick with about 4 water levels, but you could go to 36 or 32, for instance, or 120, and this here makes it really granular. So if I go down here and I have my little basin again, and I add water, we'll see that the water is a lot more like granular and small, falls in very small little bits. Now this here, if you're on a really massive terrain, it could be a massive amount of computational power required to do this. But you can see that the difference between the high level and low level allows you a lot of freedom of choosing, do I want 30%, or maybe I want to reduce the water by a fraction every certain amount of time. Allows for more of these elements, but it comes at a computational cost. So let's, yeah. So this here allows us to pretty much quickly build a pressure model where your water could flow from a lower level to a higher level and stay at a fixed level. Now, this algorithm does have one problem, and that is the edge cases right here. So the potential of this is this y-axis plus 0, and this here is y-axis plus 1. So the potential for water to fall from here to here is limited, and it doesn't know that it should go down this path, and nor should it. If you have like a wide path down here, you kind of spread the water out a little bit like this. It won't know that it needs to go into this direction to fall down into this hole. Now, you could move this up into, if you were to change this to like 1, you'd see a little bit of a different behavior that would solve that problem. So let's go real time. You end up with something like this down here, where the water keeps moving. And if the water keeps moving, if you have it on like a flat surface, it will eventually move to a location that falls down. So you can see the water here, it just jiggles, and it will eventually jiggle all the way to the edge, maybe. In this case, it seems to be a stable state, but if I added water on the edge here, you can see that the water doesn't stay on the edges anymore. So you can see, yeah, the water fell from here and eventually found a stable state where it eventually fell down on the side. So that's one thing that you can do, but what you end up with is this traveling water on the top layer. And that may not be a perfect, or it may not be a problem with whatever game you're building, but it definitely isn't pretty. The other thing is that if you had a stable state where you didn't have any water moving, you could compute what your candidate's better. We know that we have these two puddles right here, so what we can say is that whenever a water level change, that's whoever's connected to that change will be able to receive or will be able to move, but any group of water that didn't have any movement at all would be considered stable, and you wouldn't have to recompute any of the water physics there. So yeah, making this 2 here, we end up having this stable state where we can eliminate a lot of computation by saying, you know what, we know you're not moving, so if you hadn't moved in the previous iteration, we're going to consider you stable, and we won't recompute this section of the graph anymore. So that kind of concludes this water physics. I hope you enjoyed the code right here. It took a bit of time. I did read up on a lot of like my inspiration comes from Dwarf Fortress, and they do have a water pressure model. They had an article on the water pressure, and a lot of my inspiration came from that article. So you can see here they were talking about the waterfall effects. This article definitely is an interesting read on how the water physics works and some of the problems that they were trying to solve. I ended up doing it slightly differently to avoid this particular problem. So I'm pretty sure that the algorithm that I chose is very different than the algorithm that Dwarf Fortress uses. But this article does go into a bit of detail on how to model water physics. That would be a slightly different take on my own implementation. All right, well, thanks for watching.